Okay, so I think we kind of figured out the linear autoencoder, where we're mainly interested in like the concept of like where our data is images. And so I mean basically if let's say we vectorize the images, like the main observation is that the only thing that the model can output is linear combinations of the decoder weights, right? So, like, for instance, this, I guess, like red. Let me turn off nightlight. Okay, so like this red. These are red weights emanating from Y1, and so that's like you can interpret that basically as a dictionary image or a basis image, and so yeah, I mean like just from inspection, this vector is always going to be some linear combination of the vector in green and the vector in red, which are the weight vectors. Yeah, so like explicitly y sub 0 is a scalar, so on and so forth. So, which means that like the output is always going to be in the linear subspace, like of dimension, I guess like however many latent variables you have, modulo the linear independence of the vectors. But anyway, so so that's kind of like the first rule of linear autoencoders is that like so in particular like I guess that's the thing that would like have to happen in training is gradient descent would have to find weights for the decoder weights such that every data image is a linear combination of those decoder weights. And then the second thing that has to happen is that, like the encoder has to work, so like if you, I mean, like by assumption, you have to have data that, is this linear combination. And so it's the job of the encoder to find the weightings, the y sub 0 and the y sub 1. And I believe it can do that by, simply multiplying or taking the dot product of the decoder vector, like each decoder basis vector with the input, and like that directly gives you the weighting, which I think is like I think that's true, but so anyway, so in particular, it turns out like if the encoder weights are, just the transpose of the decoder weights, then you have a working linear autoencoder given that, all your data are representable in this way. So I suppose like it's not necessarily clear that like gradient descent would always find the weights Although, I mean, like, the problem might even be convex, and so then I guess, like, you do have some sort of guarantee that gradient descent will find the weights. I think the thing, though, is that, like, if you're interested in the concept of, like, generating images, like a style GAN, like, the decoder would be the style GAN part of the model. The thing that happens, though, I think empirically, is if you try to, like, just generate random y0, y1, you're going to end up with an image that does not look, that typically does not look correct. And so I think basically that means that, like, the, I don't know, cluster of natural images, they may be contained within, like, the span of the decoder weights, but that span is actually, like, enormous, and the actual, like, natural image cluster is, like, exponentially small in terms of volume. So the idea of, like, uniformly randomly sampling a latent code and then expecting to find a natural image doesn't work. And yeah, I mean, like, there's also kind of the question of, like, yeah, I mean, like, what aspects of the data are being stored in the decoder weights? And I kind of feel like that's almost arbitrary. I mean, like, it just, you could almost have, like, the decoder weights be random, and yeah, I don't know, as long as they span, as long as they contain the data cluster, then like, the autoencoder should work. So now, like, when you add non-linearities and also, like, multiple layers, then yeah, it's not entirely clear what's happening anymore. Yeah, let's do, like, ways. Okay, let's do, like, image generative image models. Alright. Are we gonna do, like, a brain dump of generative image models? Okay, so one is, like, autoencoder style. But like, ideally would find latent code space such that uniform random sample from space maps to a realistic data element. However, linear autoencoders only find a linear subspace containing the data cluster. Most points do not correspond to realistic data. Okay. There are, of course, GANs. And then there's, I guess there's like autoregressive. Such as like a transformer. Then there is kind of like super resolution models. Super resolution. There's something like learning or like denoising models. And then I guess, I mean, there's also kind of like, conceivably, there's like physics-based graph physics-based I was trying to think though, I mean, like for the autoencoder style model, yeah, like would there be a way to, I mean, yeah. Okay, so anyway, that's the yeah, I guess like the I guess understanding of like how an autoencoder, linear autoencoder would work. You know, I mean, ultimately it can only output linear combinations of the decoder weights. I mean, even if you have multiple layers, I mean, still the final layer is going to be, you know, some linear combination of the decoder weights. And I'm trying to think, like, to what extent that's true for, like, a convolutional layer. I mean, I think it's I think it's also kind of true for a convolutional layer. But yeah, I'm trying to figure out if I want to think about that or if I want to look at setting up a transformer. Yeah, I think I'm gonna do 10 minutes on trying to get a transformer running, like any transformer style model running in a Colab notebook. So that'll be our goal. For the rest of the video. Any like pre-trained transformer doing any task, preferably as small as possible. So I think we'll just search the internet to see what we have going. Like transformer in a Colab notebook. Okay, Hugging Face. I've heard about these. So I'm guessing you're just going to so yeah, I mean, like, I guess Hugging Face is like the main kind of thing. Is there not what if you go to TensorFlow Hub? Whoa, spell it correctly too. C models. Exactly. Text problem domains. Generation. There you go. But want them to be as small as possible. Sentence fusion. Machine translation. Seek to seek. Extreme document summarization. Document highlights. Machine translation. TF2? Oh no. Yeah, it doesn't look like they have like TF2. Alright, we found a collab notebook. Yeah, I'm just gonna go through this later.